So in our study of digital circuits, we've now progressed pretty much to about the pinnacle of what we're going to see. We're talking about not only sequential devices, which involve memory of some sort. In our case, we'll be looking at 3 bits of memory. But we're not only analyzing those devices, now we're designing them. So we're doing something from scratch. We're creating something that didn't previously exist. And in lab today, you're going to be doing 2 digital designs. You'll actually do the design as a pre-lab, and then you'll come into lab and ready to build the circuits right here in class. So please remember, a very extensive pre-lab for this one. This one is probably going to take you at least an hour to do these 2 designs. The first design is to build what I'm calling, and I don't think this is the official name, but I'm calling it an even-odd counter. So it counts up in even numbers first, and then it counts up in the odd numbers. Then it goes back to the even numbers, and then it goes back to the odd numbers. So really, it's just a matter of a particular sequence of numbers, and you can see the sequence 0246 1357, 0246 1357. So your first step then is to show the state diagram, and you can do that in this space right here. Then this is the big table. So you got to fill in the big table with the next state for each state, the transitions, the conditions, and then the JK inputs. Then use the JK inputs to fill in these Carnot maps. Once the Carnot maps are complete, you can solve them to figure out what each of the variables is supposed to be, and then draw the circuit diagram down here. Now the circuit diagram, you don't necessarily, I want you to show that there'll be 3 flip-flops. There'll be Q sub C, there'll be Q sub B, and there'll be Q sub A. I want you to show me that there's a clock signal on each of them, and show me that there's a clear bar input on each of them, but you don't necessarily have to show the connections to those, because that's going to perhaps make the circuit very cluttered. Also in this case, if you have an AND gate or an OR gate, you don't have to necessarily route it back to the outputs. You can just show what the inputs of the AND gates and the OR gates are. Now, the next step then is to figure out how are you actually going to build this particular device. And we have here the pinouts of a 7473, and we have the pinouts of a 7408, and we have the pinouts of a 7432. Now you're going to have 2 of the JK flip-flop chips. So you'll have a total of 4 JK flip-flops. You're only going to need the first 3 of them, and then you're going to have a total of 4 AND gates and a total of 4 OR gates. You won't need all of those either, especially for this first circuit. Now, the first thing that you're going to need to do is, the next thing you're going to need to do is go back to the previous figure, the one that you just drew, and add the pen numbers. So, for example, when you showed the first flip-flop, that's going to be, the J input will be pen 14, and the K input is going to be pen 3, and the Q output, that's going to be pen 12, and the Q1 or the Q bar output, that's going to be pen 13. Now, you're going to have 2 JK flip-flop chips, so you might want to reference that as like chip number 1 and chip number 2, for example. You want to distinguish because the Q sub C will be the left half of the first chip, Q sub B will be the right half of the first chip, and then Q sub A will be the left half of the second chip. We're not using the right half of the second chip. So just be careful when you're numbering those pens. The Q sub C and the Q sub A will have the same pin numbers, and then Q sub B will have a different set of pin numbers because it's the right half of a chip. Over here on the AND gates and the OR gates, remember that it goes 1 and 2 gives 3, 4 and 5 gives 6, but then on the top it reverses, so that 13 and 12 gives 11, 10 and 9 gives 8. I suppose it only reverses depending on how you think about it, but it's important to realize that that's what the pinouts are actually going to do. So I would encourage you to also, for each AND gate, put a 7408 inside of the AND gate, and then number the pens that you're actually connecting to it. This will make it much easier for you when you get to lab. And then similarly for the OR gates, put a 7432 inside of each OR gate, and then the pin numbers of the devices that you're going to want to connect to that. So that's really what you're going to need to do for the pre-lab for this one. When you come to class, you're going to want to check with your lab partner and see if you both got the same solutions for the J's and the K's. If you didn't, track down which one is wrong. Perhaps the professor or the teaching assistant can help you. Once you've agreed on a solution and you're confident that it's a good solution, then you want to build it. So you construct the circuit, verify that it's operating correctly, and then demonstrate it to your professor. There's not a whole lot in lab. I mean, wiring these devices up is going to take some time, so that's why we have the extensive pre-lab. Pre-lab number 2 is going to be a Modulus 6 counter. So it's going to count 0, 1, 2, 3, 4, 5. So that's 6. 6 different states. That's why we call it Modulus 6. And then it goes back to 0. Remember that a regular counter, a regular 3-bit counter, would go up to 7 and then back to 0. But here we're only going up to 5. Very important. If the device finds itself in state 6 or in state 7, then it should also go straight back to state 0. You might say, how in the world could that happen? It's not 6 and 7 are not part of the sequence, but when the device powers up, it is possible for it to enter into one of those states by random chance. When you watch the demonstration video, you'll see that I actually powered up into both of those states. If that happens, you don't want the case, for example, where state 6 goes to state 7 and state 7 goes to state 6. That would give you an alternate sequence of 6, 7, 6, 7, 6, 7, and you definitely don't want an alternate sequence. To ensure that that doesn't happen, we're going to make sure that state 6 goes to state 0 and state 7 goes to state 0, and then we'll just start the normal sequence of going from 0 up to 5. So that's an important thing to remember in doing this design. So here we're looking for the state diagram. And then once again, use the state diagram to fill in this table, use the table to fill in the Carnot maps, and then use the Carnot maps to draw the circuit diagram. Again, now please be sure to include the chip numbers and the pin numbers for each input and output so you can be sure that when you get to lab, it's going to be easy to build the circuit. And then testing it, pretty much construct it, make sure that you and your partner have the same design, construct it, and then you're ready to go. In the off chance that you have extra time at the end of lab, you can go ahead and build the Modulus 8 counter. So that's just a standard 0 through 7 counter that repeats 0 through 7, 0 through 7. This was actually the subject of an example problem in yesterday's lesson, so you don't need to do the design. This would just be one more opportunity for you to build a circuit and verify that it does what it's supposed to do.